Alright, so this is a 12th video in the series of name reactions, and today we will discuss Bamford Stevens reaction. So I will discuss everything in detail from basic to advanced. So in this reaction, the starting material is called tosyl hydrazone, and the product is alkene. And the reagent we need is simply a base in present of solvent. So this is a general reaction. In Bamford Stevens, you convert tosyl hydrazone using a base under a particular solvent to get your product alkene. Now what is the structure of tosyl hydrazone? So this is what we call the tosyl hydrazone, and this much part is what we call the tosyl, and this much part is what we call hydrazone. Okay, now the reaction is very well dependent on solvent. If your solvent is a protic solvent, the reaction goes via carbocation intermediate. If your solvent is aprotic, the reaction goes via carbene intermediate. Okay? So now let's spend some time discussing protic and aprotic solvent. So as I have said, the reaction is very well dependent on the solvent. So if your solvent is protic solvent, the reaction will go via carbocation intermediate. Now, what are the protic solvents? So in a protic solvent, you will have replaceable H plus ions. So example of protic solvent can be water. You can have formic acid, or maybe acetic acid. You can use ammonia. You can use alcohols like methanol, ethanol. You can also use hydrofluoric acid, hydrochloric acid. So all these solvents will have replaceable H plus ions, and they come in category of protic solvents. So the reaction intermediate will be carbocation. Now when you have a solvent which is aprotic solvent, the reaction intermediate will be carbene, right? And there will be no protic solvent, no H plus ions in the system. The example can be acetone or DMSO as a solvent, dimethyl sulfoxide, or you can use ester as a solvent. So you see, all in this we do not have the H plus ions. For example, if I take acetic acid, okay, so this is a acetic acid, and we have a replaceable H plus ion, that's why it comes under the category of protic solvent. But the moment I make it ester or maybe acetone or DMSO, we do not have the replaceable H plus ions. That's why it is an example of aprotic solvent. More example can be DMF, dimethyl formamide, or maybe acetonitrile as a solvent, or 1,4-dioxane. So these are the examples of aprotic solvents, and if you see these solvents in your arrow or the reaction condition, you should know that the reaction is going to go via carbene intermediate. Now let's spend some time discussing carbocation and carboanion. I mean the carbene. Okay, so what is a carbocation and a carbene? So we know that carbon can form 4 bonds. Okay, so let's say it forms bond with A, B. So I have already taken C, so let me write D and E. Okay, so carbon can form 4 bonds with 4 atoms, and each bond is representing 2 electrons. To generate carbocation, the atom A is going to go by taking both of the electrons, and this is how you generate carbocation. If one of the atom goes away taking both of the electrons of the bond, it will generate carbocation. Now, what is carbene? So carbene comes from carbanion. So what is a carbanion? First we need to look into that. So once again, carbon, here we have a D. So once again, carbon is forming 4 bonds with A, B, D and E. To generate carbanion, this time the A is going to go without taking the electrons. So in carbocation, the A was going by taking both of the electrons, but to generate carbanion, the A is going to go alone and will keep both the electrons on C itself. And this is how you generate carbanion. So this is my carbanion. Now carbene is generated from carbanion. And to generate carbene, another atom is going to go by taking both of the electrons, just like in the case of carbocation. And you will generate carbene. So this is what we call the carbene. Okay. So let me just quickly revise. So to generate carbocation, one of the atom is going to go taking both of the electrons, and you will generate carbocation. Now carbene comes from carbanion. To generate carbanion, the A is going to go keeping both of the electrons on C itself, and you generate carbanion. To generate carbene from carbanion, another atom is going to go by taking both of the electrons with itself, and you generate carbene. Now carbene is a neutral molecule. You see, carbocation is a positively charged, carbanion is a negatively charged, but the carbene is a neutral molecule. It can act as an electrophile, or it can act as a nucleophile under the given condition. Carbene can exist in a singlet form or in a triplet form. We will discuss carbene in future when I will discuss reactive intermediates. So we will discuss carbene in detail at that point. So for time being, this is enough to know the basic of carbocation, carboanion and carbene generation. Okay, so in a Bamford Stevens reaction, we convert tosyl hydrazone into an alkene using a base in a solvent. If the solvent is protic solvent, the reaction goes via carbocation. If solvent is aprotic, the reaction goes via carbene intermediate. What is the structure of tosyl hydrazone? I have already discussed. Okay. So in exam, you may not be directly given tosyl hydrazone. You might be, you have to make it in the reaction. So let's discuss the retrosynthesis of this molecule. So as I said, this part is the tosyl part. So let's break the molecule from this part itself. So I'm doing the cleavage at this point. Okay, now nitrogen will attack at sulfur, so something has to leave. So I'm going to keep a leaving group, chlorine here, and this is what we call tosyl chloride. Okay, and the other part we will get. So here we are going to generate NH2. This imine, and we know that we can generate imine from this part if I keep a ketone here and react it with amine. So this will give me, so this is going to be NH2 and the other part will be ketone. So this is my hydrazine. So this molecule is called hydrazine and this is my ketone. So this was the retrosynthesis for tosyl hydrazone. First we break bond from here, keep chlorine here and NH2. So one part is tosyl chloride, another part we got this imine. We can break the bond from here, okay, and we generate hydrazine and a ketone. Now let's look at the forward organic synthesis for this retrosynthesis. Okay, so we have a tosyl chloride. And first we will react it with hydrazine. Okay, so this nitrogen lone pairs will attack at this sulfur, and then through conjugation this Cl is going to leave. So we generate so we have NH2 here and one NH2 here. This nitrogen will get positive charge. So we just removed Cl, that Cl is going to come back. We'll take this proton, will neutralize nitrogen and we get this one. Okay. In second step, we are reacting it with ketone. And we also need a mild acidic media to do this reaction. And the product we are getting simply when we have primary amine and we have a ketone, we simply form imine bond between this nitrogen and this carbonyl. So let me show you the mechanism for this second step. Okay, so we have a ketone, right? And we have a mild acidic media. We have hydronium ions in the solution. So this oxygen right here can grab this proton and can remove water molecule. And this has activated my carbonyl carbon. So this is the first step where ketone takes the proton from hydronium ion, removing water molecule. Okay, then we have this tosyl hydrazone. So let me write that. So in the first step we have generated this one. So this nitrogen lone pairs will attack at this newly generated carbonyl carbon, and this bond is going to neutralize. So this will give me R1. This part is same. We have OH here now. We have NH2. So this nitrogen is right here. This will get positive charge. Now this is connected with NH, and that is connected with SO2, benzene ring, and at para we have methyl. Now the intramolecular hydrogen transfer will take place. So this oxygen will take the proton of this nitrogen and will neutralize. So this will give me, so this has become OH2. And here we have NH, NH, S double bond O, and rest part will be same. Now at this point of time, so we have removed water molecule here that can come and act as a base, taking this proton right here. And this bond is going to fall here and water molecule is going to leave. And guess what? We have generated the product. So we have a double bond now. And this is the product. So now you can generate your tosyl hydrazone, the starting material for the Bamford Stevens reaction. So I have shown you the retrosynthesis and the forward organic synthesis as well with mechanism. Okay, now let's write the mechanism for Bamford Stevens reaction. So we have a tosyl hydrazone. We need base in a solvent and we generate alkene. So let's write mechanism for this one. So this is my tosyl hydrazone. Okay, and we have a base. So let me write my base here. So base will have this lone pair of electrons Okay, the example of base can be HO minus or any base you can select. So this base will grab the proton from this nitrogen and will generate carbanion. Now the question is why it has taken the proton from this nitrogen, because if we generate carbanion here, that can be stabilized through conjugation of this SO2. So that's why the base is going to go and grab the proton from this nitrogen. So we have a carbanion right here. Okay, so this carbanion can be stabilized through conjugation with this SO2. So it's a pretty stable nitrogen anion. Now this nitrogen has a lone pair of electrons because it is forming 3 bonds. So this nitrogen lone pair can form double bond here, and this whole tosyl group is going to leave. And we're going to get, so now this part has gone, right? And we have nitrogen with a negative charge, double bond nitrogen. Nitrogen with a negative charge, doubly bonded nitrogen, which is further doubly bonded with this system. So this nitrogen is forming 4 bonds, so we'll get positive charge. Now this molecule has a negative and a positive charge in itself. So this is a neutral molecule, which can be written as this one. Okay, so this is the first step where when we react tosyl hydrogen with a base, we get this molecule, a kind of diazomethane type of molecule. So in first step, base is going to grab the proton from this nitrogen hydrogen. We generate this nitrogen anion. So this is the main step. So this imine nitrogen, using its lone pair, will form a double bond here. This whole tosyl group is going to leave and you generate this particular system. So this nitrogen A is right here. Okay, and this nitrogen B is here. So we have a double bond between nitrogen A and B, and this part is still the same. And you get this neutral intermediate. So this was the mechanism in the first step using base. Now in second step, the solvent is going to come into the picture and will decide whether the further reaction is going to go via carbocation or the carbene. So let's look into that. Okay, so we have generated this intermediate in the first step. So let's write the mechanism in protic solvent. So where we have H plus ions in the solution. Okay. So this nitrogen with a negative charge will form triple bond here, and this bond will grab the proton. Pretty straightforward. So this nitrogen is forming triple bond with this nitrogen, and this nitrogen still have a positive charge. And this carbon is now bonded with this hydrogen. Okay. Now this is a N2 molecule. This can leave as a neutral gas, and we will generate a carbocation. So that is why when you are using protic solvent, you generate carbocation as an intermediate. Okay, and then this hydrogen is going to go forming double bond here, and you generate alkene. This hydrogen can be taken by the base present in the first step. Okay, so this is how you generate the alkene. Now this alkene can be cis or can be trans, simply because the carbocation is a planar molecule. So that's why we have a 50-50% chance of generating both cis and trans. So this is mechanism in protic solvent. What if I do the same reaction in polar aprotic solvent? So once again, this is my intermediate from the first step. Right? So in a polar aprotic solvent like TMF, TMSO and all, we do not have H plus ions. So reaction will still go in the same way. This nitrogen will form triple bond here. Just because we do not have H plus ions, this bond will fall on carbon and will generate a type of carbanion. So we have a carbanion. And remember, carbene is generated from carbanion. And when we have a carbanion, and an atom goes away taking both of the electrons, so N2 gas is going to release and carbene is going to form. So this one is carbene. Now at this point of time, now pay attention here. So this hydrogen with both of the electron will migrate towards this carbon. So this carbene will again convert it into carbanion, and that carbanion will be used to form double bond here. And this is how you generate the product. So I repeat, this hydrogen, this complete bond is going to migrate towards this carbene carbon, and that carbene will be converted into carbanion, and that carbanion electron will be used to form double bond here. And this is how you generate the product. Okay, so that's it for today. We looked deeper into the Bamford Stevens reaction. Please share and subscribe. Thank you.